recall energy in the electric field. We discussed that by considering a charge process of a capacitor. The amount of work done to charge the capacitor equals to amount of energy stored in the capacitor. As a result, an electric field is established, and the sum of the chemical potential energy in the battery is transformed to the electric potential energy of the field. In an analogous way, we will find energy in the magnetic field by considering a circuit containing an inductor. Recall this equation for a RL circuit. From this equation, we understand that with an inductor, a battery must provide more energy. Part of energy is stored in the resistor, and the remaining energy is stored in the magnetic field of the inductor. We know an inductor will oppose the change of the current passing through it due to the inductance. Therefore, the work must be done by a battery to establish a current in the inductor. Based on the work-energy theorem, energy will be stored in the inductor. This is analogous to that of a capacitor in the electric case. We multiply each term of both sides of this equation by the current I and rearrange the expression, and we have this one. Let's see the physical meaning of each term in this equation. I epsilon represents the rate at which the energy is supplied by the battery. I squared R is the rate at which the energy is stored in the resistor. Li di dt is the rate at which the energy is stored in the inductor. In other words, this term represents the rate at which the energy is stored in the magnetic field. We use the symbol U to represent the energy stored in the inductor at any time. Then we have this equation, du over dt equals Li di over dt. Cancel dt and integrate du to obtain the total energy stored in the inductor. U equals to 1/2 Li squared. Recall the energy stored in the capacitor. These two equations have the similar mathematic form. Similar to the energy density of an electric field, the energy density of a magnetic field can also be determined. To determine the energy density of an electric field, we use a simple case, a parallel plate capacitor. So here, let's consider a simple situation, an ideal solenoid. The magnetic field an ideal solenoid is given by this one. B equals mu0 times N times I. The inductance of an ideal solenoid equals to mu0 times N squared times V as obtained earlier. Substituting the expressions for L and I into the equation of U, and we have this one. Therefore, magnetic energy density or energy stored per unit volume in the magnetic field of an inductor is this one. Although this expression was derived from the special case of an ideal solenoid, it can be applied for any region where a magnetic field exists. We notice that this equation is very similar in form to the equation for the energy density in the electric field. In both cases, the energy density is proportional to the square of the field magnitude. So far, we have learned that a resistor, a capacitor, and an inductor could store energy but in different mechanisms. Please give your ideas about energy storage about these three different circuit elements. This is an assignment for you. In the next lecture, we are going to discuss the last part of this course, Maxwell's equations.